We've begun studying solutions to systems of linear equations in this vectorized or parameterized form. And we have some idea what the geometry looks like. What I want to do here is compare two types of systems, non-homogeneous and homogeneous. So the system on the left, x plus 4y equals 2, 2x plus 8y equals 4, is called non-homogeneous. And I'm going to write this right here, non-homogeneous. And the system on the right, you'll notice, is the same set of variable relationships, x plus 4y and 2x plus 8y. The only difference is that the right-hand side, the constants, are both 0. And when that occurs, you have what's called a homogeneous system. Now, the key here is that the vector b, as we're referring to it here, may or may not contain one or more zeros. So even if one of these was 0, b would still not be the 0 vector. For example, if this was 2, 0, then, well, not quite the 0 vector, because the 0 vector requires that both components, or if there's more than two equations, that all the components be 0. So that's the only difference between these two systems. And if we were to perform row reduction, Gaussian elimination, get the reduced row echelon form, we would get something that would look like this for the non-homogeneous system. And we begin analyzing it, writing the solution for it. What we see is that since there is, and we'll call this x, y, and our constants, then we see that there is a leading 1 in the first row under the x column. There's no leading 1 in the second row. We've run out of rows. Therefore, y is going to be a free variable. So, as usual, we let y take on the value of some constant. Okay, I'll just specify that it could be any real number. And depending on what value of y you plug in, x plus 4y has to equal 2. So that means that if x plus 4y equals 2, then that means that x is equal to 2 minus 4 times whatever we plug in for y. What are we going to plug in for y? Well, here we're just calling it c, and so this would be 2 minus 4c. And we could write the solution, xy equals, x is equal to 2 minus 4c, y is equal to c, and I'll just write that as 0 plus c so that I can parameterize this and write this as two separate vectors, one containing the constants, 2, 0, and then the other one, I'll just go ahead and factor out a c right away and make this c times negative 4, 1. Okay, we have a coefficient of 1 in front of that c. Let's do the exact same thing for this system over here. Well, the only difference is that if these values, these constants, start off as 0, they are always going to remain 0 throughout the entire row reduction process. And we can rationalize that because we're either scaling rows or adding constant multiples of one row to another row, or possibly interchanging them. In either case, if you take 0 and multiply it by any constant, you get 0. And if you add any multiple of 0 to 0, you get 0 still. So the exact same process takes place, and in this case, we would get xy is equal to, well, for y, we're choosing an arbitrary constant. And here, since x plus 4y equals 0, this means that x is equal to negative 4y. Since y is set to be some constant c, this means x is negative 4c. Now the key here is that notice that both of these constants are 0. And so if we wrote this as two separate vectors, we would get 0, 0 plus c times the negative 4, 1 vector. Okay, so as such, we notice that the only difference between a non-homogeneous system and the homogeneous system with the same coefficients the same coefficient matrix, the same coefficients for x and y. The only difference is what we get as our constant vector. Right? One of them is 0, 0, and the other one is going to be, well, whatever we get when we reduce this system and deal with the non-zero constants on the right. If we analyze this more carefully, this will always be true for non-homogeneous systems, that we're going to have at least one non-zero component inside of our constant vector. And so we give this a special name. We call this x sub p. And we give this right here the name x sub h. Okay, now the reason we do that is because p stands for particular. Means it's a particular solution that is specific to the values, non-zero values that we have inside of that b vector. However that gets reduced, x sub p emerges because of this right-hand side. H stands for homogeneous. Well, why does that stand for homogeneous? Well, because notice that it will be the solution for the homogeneous system of equations where the b vector is the zero vector. So think about this as b is equal to the zero vector. It's a special case of b. And so in general, the non-homogeneous system will be the homogeneous solution plus some non-zero vector. Now, we're not going to call this xp because it is just the zero vector. And really, at the end of the day, this is just equal to c times the vector negative 4, 1. So it has no non-zero constants. Fantastic. So that's always going to be true. It doesn't matter what system of equations we pick. If we pick a system of equations and then at some point switch the right-hand side to consisting of zeros, we made it homogeneous. And we'll notice that the relationship will be that parameterized vector, the vector containing one or more parameters, will be the same across the non-homogeneous and homogeneous solutions, only difference being non-homogeneous will have this particular solution. So geometrically, we've already kind of seen what this ends up looking like. The solutions to this equation, to the non-homogeneous system, will be the vector 2, 0, which is a vector that points 2 units to the right, 0 units up or down. They'll make that look a little nicer. That's going to be the 2, 0 vector. There it is. Plus some multiple of negative 4, 1. Well, negative 4, 1 is a vector that points 4 units to the left and up 1 unit. So it would be a vector that points along somewhere along this line right there. Now, because it's any multiple of that, I'm going to draw a dotted line like this, indicating that any multiple of that will work in either direction. But the difference is that, notice that this is essentially the line y equals negative 1/4 x, but it's shifted 2 units to the right. Negative 1/4 x shifted 2 units to the right. And the difference between that and just the homogeneous solution is the homogeneous solution is any multiple of the negative 4, 1 vector. Now that's again going to be a vector that points, for every 4 units to the left there will be a 1 unit rise, so it'll look something like this. And any multiple of that will do, so it will be any scalar stretch or shrink of that. Or in this direction, trying to make it look like it's on the same line. There we go. So notice that this is exactly the line y equals negative 1/4 x. In other words, any point along this line will solve the homogeneous system. Any point along the line y equals negative 1/4 x shifted 2 units to the right will be a solution to the non-homogeneous system. So the key here is that the non-homogeneous solution is some shift of the homogeneous solution. Does it have to always be just to the right or just to the left? No, it could be that this vector right here, that x sub p, is going to have a non-zero x and y component. In fact, if we're in multiple dimensions, these could all be non-zero in practice. And the other key point that I want to illustrate is that for a non-homogeneous system, the solution will be of the form x is equal to some particular solution, this will be constants, plus some homogeneous solution, and this will contain our parameters. A homogeneous system, again, same coefficients, just 0 b vector, its solution will look like this. It will simply be x homogeneous, which is the same for non-homogeneous and homogeneous. So the non-homogeneous will simply be a shift of the homogeneous solution.